Hello, welcome to episode 2 of Stats with Mats. That's what we are going to be calling this web series from this point on. Welcome, and thank you for the feedback that so many of you offered me on both the format that we've gone with here and with the your understanding of the formula. That's something I'm going to be doing consistently going forward, right? I'm going to be trying to take the temperature of the class and really trying to understand where people stand. Today, we are going to push the t-test forward, and we are going to do the same formula, except alter it to reflect the situation that might occur where sample sizes are unequal, okay? So before I get started, today's random dumb movie observation comes from watching the second half of Titanic about a night ago. So Titanic is one of those old 90s movies that pretty much everybody has seen, even if you weren't alive when it came out in 94. After watching the second half of Titanic, now believe that while the actual sinking of the actual Titanic was a tragedy, the sinking of the Titanic in the movie Titanic is not. And here's why I say that. Because I flipped it on right at that kind of climactic moment in which the star-crossed lovers, right? The upper-class rich girl and the poor lower-class boy go up to the deck and they embrace, and she says, "I will abandon my people. I will turn my back on my class background and class identity and make a new life with you." And right at that exact moment, the ship smashes into an iceberg and begins to sink. What's this got to do with their story? Well, you have to see how these two things are connected, because I would argue the real tragedy in that movie, right, in the fictional environment of Titanic, would be if the ship made it all the way to New York, because they never would have made it, right? They never would have been able to bridge the class divide in 1910s or 1920s New York, whenever this was, and they would have split up. So in order for their impossible love to live, the ship had to sink. That ship had to go to the bottom of the Atlantic Ocean. Okay, anyway, let's go on. So as I said, we are going to be covering two means t-tests with unequal ends today. In the way of review, let's see if I can make this a little bit smaller. Yeah, there we go. Okay, so if we want to compare a sample mean to a population mean, and we know what that population variance is, then that's a z-test. If, however, we want to compare a sample mean to some type of predetermined value and we lack that known population variance, that's the one mean t-test. That was our example where we did Nicaraguan fertility, you'll remember. That's the one mean t-test with a specific formula. If we want to compare two sample means when ends are equivalent, then the two means t-test with equal ends will allow us to do that. Now, as we were working through the formula from the first time, from Monday's lecture, I should say, you should have realized that it's a little unrealistic to expect that you will always have equal ends. Like, that's just not a super realistic assumption, because population sizes are different. The willingness of people to respond to certain questions is limited. So it's not particularly realistic to assume that the sample sizes across the two samples and the two means that you want to t-test are going to be equal, right? So that's the road ahead here. We made an unrealistic assumption of equal sample sizes. If the group size differs, as you see with this picture, clearly different sizes, then we are going to have to change our formula around. We are not going to change the logic of the t-test, and we are not going to change the interpretation. So many of the steps of the hypothesis test are going to proceed as they did with other forms of the t-test. But the formula is going to have to change, okay? A word about your understanding and ability to do these formulas. If you are just watching the video, now I have no idea, I have no way of knowing how you guys are approaching this, but if you just sit down and watch this video, and you don't actually follow along with the math in your notes, I think that's a mistake. I really do. I think it's a very serious mistake, actually, to just watch and think that you have it if you haven't actually tried to write it out by hand and do the math here. So as we go forward, I'm going to continue to push ahead. But one of the advantages of this formula, even though I can't see your understanding and see your comprehension, one of the advantages that we have going on here is that you can pause this video at any time and finish the math, or kind of just stop and do a knowledge check for yourself, okay? So here's the revised T formula. I have numbered these in the order of which you actually have to do the math, okay? So let's work through this. I'm going to start with step 3 here of this formula, because that's the T formula you're most familiar with. T equals x bar 1 minus x bar 2 over s of x bar 1 minus x bar 2. X bar 1 and x bar 2 will always be given to you. They will always be things that are presented to you in the word problem. You'll have one sample mean and you'll have a second sample mean. So the numerator of that T equation right up here, that is something that is not going to be too difficult. That's just simple subtraction. The denominator of s of x bar 1 minus x bar 2 will be the square root of s squared p over n1 plus s squared p over n2. S squared p is a weighted, I'll explain this at a later point in the PowerPoint as well, but s squared p is a weighted and pooled estimate of the standard error. So we have to calculate s squared p. The number that s squared p assumes in this part of the equation right here will always be the same. S squared p is one number, and that number is calculated with the bottom formula. So that's actually where you have to start. S squared p equals n1 minus 1 times the first variance plus n2 minus 1 times the second variance, divided by n1 minus 1 plus n2 minus 1. Not coincidentally, what you're dividing this by here is the degrees of freedom for a 2 means t-test. So in order to do this, you have to be given 2 sample means, you have to be given 2 sample standard deviations, and you have to be given 2 sample sizes. That's why step 1 is going to become very important here. Step 1 of the hypothesis test, where you simply write out what it is that you know, and then being able to identify what is N1 and what is N2. If you don't, have that correct, you will get the wrong answer, okay? So I'll run through that one more time. S squared p equals the first sample size minus 1 times the first variance, right? You see how that's S squared 1. If you are given the standard deviation, no, you must square it here. If you are given the variance, well, mazel tov, go right ahead and use it. But chances are not good that you will be given the variance. You'll almost exclusively be given the standard deviation, because I am not a nice guy anymore. So you do that, plus n2 minus 1, subtract 1 from the second sample size, and multiply that by the second variance, s squared 2, and then that gets divided by the degrees of freedom, n1 minus 1 plus n2 minus 1. Then that gives you s squared p, which you will insert directly into the numerator of these 2 fractions in the second part of this formula. And that number is divided by both the first sample size, and then it's divided by the second sample size. You add those 2 together, take the square root, and that becomes s of x bar 1 minus x bar 2. It is weighting the difference between the standard errors. And once you actually finish that out, once you finish s of x bar 1 minus x bar 2, that gets plopped right in the denominator of the T formula and divided into the difference between x1 minus x2. Pause there for just 1 second. Okay. So a brief but necessary detour to try and understand how to organize your sample means. If you are given 2 samples, then in theory, x1 and x2 can refer to either one of the sample means. This can get a little tricky. So I'm going to offer you a strategy that will always allow you to pick the right critical T and organize the sample means in the correct order. First of all, you always want to keep X bar 1, S1, and N1 together, okay? And it may not matter so much which sample characteristics you classify as sample 1 and which sample is classified as sample 2, but you cannot be using X bar 1 with S2, for example. That will give you the wrong answer. So let's say if we have a situation where we're doing a one-tailed test and you are specifically asked whether one sample mean is significantly greater than the second sample mean. When you organize this, you should make the larger sample mean X1, and that implies that the critical T will be positive. I will repeat that. If you are given a directional hypothesis that one sample mean is greater than another sample mean, you will make the larger number X1, and then your critical T is positive. Your observed T must be then greater than the positive version of that critical T. If, however, you are given a one-tailed test with a less than directional hypothesis, do the opposite. Make the smaller sample mean X1, and now the critical T is negative. Finally, are you being asked to do a two-tailed test? You don't care about greater than or less than. All you care about is a difference in either direction. Then congratulations. You don't have to worry about the order at all. Make X1 whatever you want, make X2 whatever you want, and then the critical T must be either greater than the positive, or your observed T must be either greater than the positive critical T or less than the negative critical T. And the order won't matter there because both tails of the distribution will encompass parts of the critical region. Okay, we good to go forward? God, I hope so. So let's do an example that is near and dear to my heart. Previous research and a little bit of personal experience will lead us to believe that alcohol consumption is higher for those aged 21 to 25, people in their early 20s, than those aged 26 to 30, people in their late 20s. Bad news I have for you is when you graduate college, Thursday drinking just kind of stops. It becomes very difficult to justify the cost. It becomes very difficult to justify going to work on a Friday morning with a hangover. So there's many reasons to believe that young people consuming more alcohol. So here's what I'm going to do. I'm going to take two samples, one of only people aged 21 to 25 and a second sample of only those 26 to 30. And here's what I'm going to find. I sample 500 early 20s individuals. I find a sample mean of 5.2. That is the average number of alcoholic drinks consumed last week is 5.2. And there's a standard deviation here for this first sample. S1 is going to be 0.99 drinks. Now, conversely, I take a second sample, 400 late 20s individuals, and I find and calculate a sample mean of 4.1 drinks last week. Standard deviation here is going to be 1.2. So this is clearly setting up as a t-test. I'm comparing two means to one another, and I want to understand if there's a significant difference here, or this is just the result of sampling error. Because my n's are unequal, I must use the unequal n formula. 400 late 20s individuals and 500 early 20s individuals. And then finally, the last thing I want to know about, say what you know here. I want to know what type of a directional test this is. This is a one-tailed test because I am specifically saying that I believe alcohol consumption is higher for young people than young people than it is for older people. Therefore, as I said on the last slide, because I'm being asked for greater than, I am going to make the larger sample mean x1, and my critical t will now be positive. And you can see here, that is exactly what I've done. If you're wondering where that picture came from, I think I was at a wedding, and I was in my early 20s. So there you go. Okay, so this is step one. I just want to be clear. This is step one, stating what I know. N1, X bar 1, and S1, and then a second group, a set of statistics, N2, X bar 2, and S2. Okay, so let's give our hypotheses. The null hypothesis: people in their early 20s are consuming an equivalent or a lower amount of alcohol than people in their late 20s. Let me just go back to the question here. You were asked to you were told that we have reason to believe that alcohol consumption is higher for young people. So what would need to be shown true in order for that expectation to be proven wrong? Well, if people in their early 20s were drinking less or an equal amount, then it's not higher. Therefore, that becomes my null hypothesis. Put another way, mu of 1 is less than or equal to mu of 2. And then conversely, my alternate hypothesis, what is it that I am actually trying to show? I have hypothesized that people in their early 20s actually consume more alcohol than their late 20s. So H1, if I wanted to write this mathematically, mu1 is greater than mu2. The sample mean, or the population mean of alcohol consumption among early 20s individuals is greater than the population mean among individuals in their late 20s. Pause there for a second, let you catch your breath. Okay, let's move onward. So step 3 is going to set your alpha level. Now, I don't want you getting too comfortable with the idea of 95% confidence. So let's try something new. It's just going to be a new entry point on the T table in your stats packet. The logic behind finding that critical T, though, unchanged. So we want to be 99% confident. That makes our alpha level 0.01. So if you go, I'll pull out my stats packet here, and we'll do this together. If I go to the T statistic table, I can see that I need to find level of significance for a one-tailed test and an alpha level of 0.01. Now, assuming that you have that you have your stats packet in front of you, the next thing is to determine the critical region. And all we have to do there is figure out degrees of freedom, and that will allow us to go forward. So degrees of freedom for a 2 means T test, you will remember N1 minus 1 plus N2 minus 1. So you will remember that N1 is 500 and N2 is 400. Give you a minute, just a second to do this in your notes, figure out degrees of freedom. So 500 minus 1 plus 400 minus 1 is 898. Because that is such a massive amount of statistical freedom, we will simply use the row at the very bottom of the T table that corresponds to infinity. That thing you see, that symbol just below 120 that you see, that's infinity. So one-tailed test, alpha level of 0.01, infinity degrees of freedom, really 898, but whatever. And we should see a critical T of positive 2.326. Why am I specifically specifying that it's positive? Let me just go back here one moment, because I'm following my own instructions here. I have a one-tailed test that is hypothesizing greater than. Therefore, I made the larger sample mean X1, that's people in their early 20s, and that makes my critical T positive. So I must find an observed T that is greater than that number you see right there. So steps 1 through 4, nothing too crazy. It's exactly what we've done before. Just take care in identifying X1 and X2, because that will cause the math to unfold differently if you screw this up. Okay, so step 5 here, all we have to do is calculate the sample T statistic now. All we have to do. The T formula requires us to calculate S of X bar 1 minus X bar 2, which requires us to calculate S squared P. That's why you can see the numbers right next to the steps here. I'm going to start with this. I'm going to start with it's kind of step 5, part 1, and then move to step 5, part 2, and then move to step 5, part 3. So this was the point where I said I was going to speak a little bit about what the P meant. S squared P refers to what is known as a weighted and pooled average of the variance. You could also say a weighted pool average of the standard deviation, because that's what would be happening in step 2 once you take that square root of it. So what does weighted mean? Well, pooled means we're combining the variances of both of our samples. Weighting very simply means we are going to give more power to the larger sample. So I want you to take a look at what is going on here in the numerator of the S squared P formula. You will notice that each sample's variance is being multiplied by that sample size, that sample's n just subtracted by 1. So whatever that sample's degrees of freedom are. What that is doing is by multiplying each variance by its sample size, the sample size that is larger is essentially going to make the variance larger. If I multiply a number by 2 or I multiply a number by 3, you can easily conceptualize which one of those outcomes or products is bigger. It's clearly if you multiply by 3. So what you're seeing there is the n that's larger, you're multiplying that sample size by a larger number, or you're multiplying that variance, by a larger number. That increases the number, and what that does when you divide by the degrees of freedom is it draws more statistical power from the larger sample size. Why would we want to do that? Well, we know that larger sample sizes tend to have smaller standard errors. Larger sample sizes tend to be more accurate. They have tighter confidence intervals. So what this is doing, all you're doing with this is giving additional power to the larger sample and kind of reducing the importance of the smaller sample. It's not that you take it away entirely. It's that you're giving more power to the sample mean that you have statistical reason to suspect will just be a lot more accurate. Okay. And finally, do not ever forget to convert standard deviation to variance. If you forget to convert standard deviation to variance, I will murder you. No, that's not true. I'm definitely not going to murder you, but I will take off points on your homework if that happens. So what do I mean by that? Let me just make sure we're all on the same page here. You can see how this letter right here, S squared 1, S is the standard deviation. That's what you're given in the formula. S squared is the variance. So in order to do this formula correctly, all you have to do is square the standard deviation and then put in the n1's minus 1 and n2's minus 1. Okay, good to go on? God, I hope so. Okay, so let's get to work. We are going to be doing part 1 here, s squared p. So I encourage you in your notes now, try to complete this formula, please. All right, so pause it if you need some time to work through this. I suspect that you will. I'm just going to push forward in the interest of keeping the video shorter and the file size lower. Calculating the estimated standard error of the difference here will be 499 times 0.99 squared plus 399 times 1.2 squared divided by 499 plus 399. Now, I run through that calculation and I get 489.07 plus 574.56 divided by 898. All that is I'm collapsing the numerator. I'm removing, I'm doing the order of operations, and that gives me an s squared p of 1.1844. Okay, so what that means in practice, s squared p equals 1.1844. That now directly goes in the numerator, right where you see my mouse. Where is it? Yeah, there we go. It goes right here for both of these. S squared p is now the same number. So that second part of this t formula, 1.1844 divided by n1, right, which is 500, plus 1.1844 divided by n2, which is 400. Okay, so running through that, the square root of 1.1844 divided by 500 plus 1.844 divided by 400. Take a moment to work through that. Ugh. And you should have the square root of 0.0024 plus 0.0030, or 0.0735. That is s of x bar 1 minus x bar 2. All I did was take s squared p there, divided both times by each sample size, add them together, and take the square root. If you didn't get that, please go back and see where you made your mistake. Because step 5, part 3 is this is where we make our money. Calculating the sample statistic. So all this is going to be 5.2, that's x1, 4.1, that's x2. So 5.2 minus 4.1 divided by 0.0735. So pause it if you're not ready, but when you are, I sincerely hope you got the answer of 14.97. That is your observed t statistic. Good job. You're beautiful and you're gonna do great. So now our final step here is to decide and conclude. So you will remember I went to great pains to specify that because of the directional nature of this hypothesis, I must be using a positive version of the critical t. Is that sample statistic of 14.97 greater than positive 2.326? Absolutely. It sure is. So what's my conclusion? Well, with 99% confidence, we reject the null hypothesis. And we conclude that those in their early 20s are consuming more alcohol than those in their late 20s. Fucking spot on, in my opinion. Okay? Good job. let's go back through that one more time very quickly so you can see the steps here. Right? So the first thing I did was calculate S squared P. I ran through that formula to get the weighted pooled estimate of the standard error of the difference. That gave me a value of 1.1844. That number was then placed directly in the numerator of this equation here as S squared P. So I run through this formula, 1.1844 divided by 500 plus 1.1844 divided by 400, take the square root of that whole thing, and we get 0.0735. And then I ran through my T formula. Really, the ending part, the T formula, really this is just not the most important part because that's the easiest equation to do. But understand how stuff in mathematics will scaffold on each other. Understand how if you screw up S squared P, how that is going to cascade down through the rest of the formula. All our formulas right now risk that having that happen. If you make a mistake early, you guarantee you make a mistake late. And that's why I encourage you, take some care with this, right? I'm not assigning long homeworks anymore. Therefore, it will be in your best interest to check your work, right? When you submit these things, check your work and make sure that you didn't make a careless mistake, because there is not a single person in this class, myself included, who is incapable of making a silly mistake or a careless mistake. Every single one of us is capable of it. And that's why it behooves us to check our work, okay? So, wrap this up. 99% confidence, I reject the null hypothesis and conclude that those in their early 20s consume more alcohol than those in their late 20s. And that's what I got for you today. Now, to wrap it up now very quickly, this video will be posted before Wednesday night. It's being filmed on a Tuesday morning from Dr. Schoen's office. And I also will be posting your first mini homework. It will require you to do a 2 means t-test with equal ends and a 2 means t-test with unequal ends. Use the stats packet as a resource. Use these lecture videos as a way to run through it again. And you must take a picture, right? If you have a printer, great. Just print that out and take a picture of it and submit it or scan it. But actually forget it. Nobody needs to scan shit at this point. Take a picture of it. Look at the picture after you take it. I must be able to find your answers and to see your work. Please write as clearly and as legibly as you can. Some of you in this class have beautiful handwriting. Some of you do not have beautiful handwriting. You know who you are. So it's your responsibility to run through this in a legible way and to circle your answers, okay? That needs to be uploaded on the Dropbox on the course page no later than 10:30 on Friday. I will be in touch soliciting some feedback for this video as well. Thank you very much for your continued willingness to interact with me and your continued willingness to offer me feedback as we work through this. Thank you and have a great rest of your day. Bye-bye.